The Diels-Alder reaction is one of the most quintessential and meaningful, and I can't think of the word, just kind of impactful reactions to happen to chemistry. It was discovered, I believe, in the 40s. I want to say in 1950, Diels and Alder were awarded the Nobel Prize for it. But what it is we take a diene, then we take what's known as a dienophile, which is, in this case, an alkene with an electron withdrawing group to make it electron deficient, so it wants these electrons. What it does is it forms a six-membered ring where we have one alkene here, and then we have our electron withdrawing group or any other substituents we had there unaffected. So it's a great way of making carbon-carbon bonds, specifically in rings and cyclic systems. And so what we have here is it is a concerted one-step reaction where our electrons move like this. So I'm going to erase this here so we can see which are the bonds we just formed, because that's important for when you're doing a retro Diels-Alder as well. You're trying to figure out what this was made with. As you can see here, these red bonds are the bonds we created, and the original black bonds are ones that were already in place. So what does this look like? First of all, if you notice here, this is a cis diene. We need a cis diene. This can't work with a trans diene. Now, if you have a trans diene like this, that's fine because it's going to isomerize to the cis version so it can react. However, if you have a cyclic trans diene, that's not going to react. It can't isomerize. It's locked because of the lack of rotation in the ring. And then conversely, if we have a cyclic system like cyclopentadiene, where it's locked in that cis conformation, it's even more reactive because we don't have to worry about it isomerizing. So the reason this works is we have the orbital overlap. Now I'm going to try to draw this instead of top down, kind of head on, but bear with me and my lack of art skills. So we have our cyclopentadiene like this, not cyclopentadiene, our diene. We have our orbitals, our p orbitals, okay? Now the way this forms is we have our dienophile with those p orbitals as well. And these, actually I got to draw this a little further under it. The dienophile gets under it, where we have this orbital overlap there, and that's what creates those new bonds. And then, say we have our electron withdrawing group, which say is carbonyl of some sort, but it's just unnamed carbonyl for right now. There's going to be secondary orbital overlap as well, which is going to further enhance the rate of this reaction. And then something else we can do to enhance the rate of this reaction, we can throw an electron donating group on our diene, because it's going to, electron donating group. It's going to just pump more electrons into our diene for reacting. And because of this orbital molecular geometry during this transition state with our orbital overlap, especially if there's this secondary orbital overlap involved, we get what's known as the endo rule. So when we create these, and you see this more when you have two cyclic structures reacting, if we can think of our cyclohexene like this that we now created, the endo rule is we're going to have our electron withdrawing group, or just whatever we had on there, going to be facing down. And that is because of that orbital overlap. Because the red is our diene and the black is our dienophile, had to position itself under that, so when they form that bond, it just pushes down. And you can see that with some cyclic systems as well. Think of, we have cyclopentadiene, and we have, say, maleic anhydride, which is a classic example of Diels-Alder reaction. What do we get? We get this right here, where we have a bridgehead carbon. We have a bicyclic system, actually a tricyclic system, and we have the whole of the maleic anhydride pointing down because of that endo rule. Oh, forgetting R. Now, Diels-Alder's products can retro. If you heat this up enough, it will, what's known as retro Diels-Alder, and we get a reverse of what we have up here, where all the electrons go back to their original place, and the reaction goes this way. And that can be done like by adding heat. So that's why typically Diels-Alder's products have a hard time in the GC, because if the GC heats it up during the ramp to get rid of any solvent, you're also going to retro your Diels-Alder adduct, and you're just going to come out with your starting materials. Now, there's a couple other things to note with your Diels-Alder. Remember, you have your orbital overlap, but when you, with your dienophile, say you have, we'll have this cis-butadiene, and for a dienophile, we're going to have this ethylene with carboxylic acid on each end. Now, this will make a cis cyclohexene, where these carboxylic acids are on the same face. Okay. Now, say we swap that, and we have a trans dienophile. What does that give us? Well, that gives us a trans cyclohexene. Oh, I can't draw a cyclohexene. That's a terrible cyclohexene. That seems to be the best I can do right now. So it's important to take note of the arrangement of any electron withdrawing groups, or just really any substituents in general, when you're looking at your dienophile. Remember, your diene, that's locked in that cis conformation. Say we want to put a methyl group on here. Okay, that's all that's happening. That's not going anywhere. Now, where things get a little interesting is when we have things that buck the trend of the endo rule. So, and where you see that is just something where, if say we replace cyclopentadiene with furan right here. Furan's aromatic, which makes it pretty stable compared to cyclopentadiene, which has a lot of ring strain. So when you make that Diels-Alder product, you're actually relieving a lot of ring strain. We're going to keep our maleic anhydride here because it just works, and it works real good. So what happens with this? So initially we form our endo product, because remember, there's the orbital overlap, and then there's that secondary orbital overlap, which makes it form much faster. However, this isn't terribly stable. So if you put enough heat into this, and there's a lot of essentially what are 1,3 diaxial style interactions that make this kind of high strain ring. And if you put enough heat in this, this will retro back to our regular our starting materials right here. And then what you're going to start to see happen is you're going to form the endo product, actually. So let's see if I can do this. I think I'm a little out of the frame. Let me push this up a little bit. We're going to form our exo product, where the ring is facing up. You're going to forgive me, I'm running into my other ring there, where the ring is facing up. And now this is much more stable. The barrier to this, to retro Diels-Alder, is much higher. And whereas this is a pretty low barrier to retro Diels-Alder, back where we regain this aromaticity. Where this one, the barrier is much higher, so it's less likely to retro. So if you want that just the endo product, that's kinetic control. You do this at low temperature, and you cut the reaction off early. Don't let it really have a lot of time to react. However, if you want to get this exo product, you react it at higher temperatures. It's going to make it retro, and it's going to start pushing it towards this more stable thermodynamic product, and you give it longer time to react so it can equilibrate to this product right here. And then you're likely going to get a little bit of a mix, but you can separate those out using a column. And so that is your endo and exo rule. Now you might see these drawn a little differently, and that's okay because it's confusing, because that's the side-on view, you're usually used to this top-down view. And we can show you like this. So if we have, say, that product that we just drew with the furan and the maleic anhydride, we're going to draw the endo product, okay? Where it's facing down. All right, with this facing down, maybe a little more. That's not close enough. There we go. What is that equal to in terms of a top-down look? So we have our cyclohexene right here. Now our bridgehead oxygen is coming out at us. So, oh wow, all over the place. So we're going to put that on wedges so you know it's coming at us. Now these are going down, so we need to put these on dashes. Then we simply just finish off our maleic anhydride portion. And those are equivalent. So if you're not used to seeing it like this, that's fine. Just know this is what it looks like from the top down. A lot of time it likes to get displayed like this to really emphasize that endo versus exo orientation, or just it kind of looks neat like this. I can't really lie to you. Now there's even further you can dive into Diels-Alder if you're going to take a physical organic chemistry class, say in upper level undergrad or you're in graduate school, that delves into even more of this with your molecular overlap, such as your HOMO, your LUMO, et cetera, et cetera. But for right now, this is what you need to know for your organic chemistry class. If you want to get more organic chemistry learning, be sure to hit that follow button.